Hi guys, welcome to again to my channel. My name is Malasa. Today I'm gonna be showing you the design of beams of the 20-story building using ETABS 2060 as per the Ethiopian Building Code of Standard and the European Building Code of Standard. In the previous tutorial, that means in tutorial part 18, I have already shown you the detailed design of column. So if you like my video, don't forget share all my videos to your friends so that your friends will be getting more relevant videos which has been already prepared with reference to this 20 story building using ETABS 2060 as per the Ethiopians and the European Building Code of Standard. So if you are a newcomer for this channel, just don't forget subscribe my channel so that you'll be getting more relevant tutorials which have been already prepared in previous time and also which will be prepared later. So don't forget providing me your questions and your comments regarding to the design and the modeling of the reinforced concrete structures and also steel structure so that I will be providing you an immediate response for your questions and your comments as much as possible within a short period of time. So if you want to get a notification for videos which will be uploaded later, just you can press the bell icon. So now let's proceed to the today's tutorial, which is tutorial part 19, which will be focusing on the detailed designing of beams. Okay, here we have already the model of this 20-story building, which have been already modeled and designed before. And I have already run the analysis and designs the frame using ETABS 2016. So now today I will be extracted all the outputs of beams and I will be preparing the detailed working drawing of the beams. So now I have already selected one sample beam here at the basement. Just we can take this beam as a sample beam so that all the rest beams can be designed according to the design principle which will be applied for these beams. So here in order to see all the results of the outputs of ETABS, just we can right click here so we can use the envelope report here. So ETABS 2016 concrete frame design provides the detailed design output reports of the selected beams. So here, as you can see here, just we have already briefly discussed the design parameters of columns in tutorial part 18. That means the what does the level mean and what does the element, the unique name, the section ID, the length, and the live load reduction factor. So and also when we come to this section property, the width of the beam, the height of the beam, and B1, that means the width, and ds is it is the all those dimensions were described in tutorial part 80. So you can go back and check the tutorial part 18. So so in order to save time, I will not go in depth for the elaboration of all those results. So I can go directly to the flexural reinforcement for major axis, and that means MED3. So what does the major axis mean and what does the minor axis mean? So we have already we have already seen in tutorial part 18. So you can go back and visit the tutorial part 18. So here we have the sorry, now let me okay here so the in the eye rebar area in millimeter. So we have two ends of beam. Suppose here this is the selected beam, and we have the end I here, and we have the integer here. So the top positive axis mean just if we take a section at this point, that is if we take section AA, so this is, it is section AA. So it has a neutral axis here, that is neutral axis. So positive 2 axis means here this is axis 2 and this is minus 2 and this is positive 2, which is located above the neutral axis. So top positive 2 axis has 498 millimeter square reinforcement area. So the top parts of the beam needs 498 millimeter square, and similarly at the bottom, that means at minus 2, here the reinforcement here is, it is 498 millimeter square, and here also it is 498 millimeter square. That means here 498 at the top and 498 at the bottom. So it is closer to the support, meaning here we are already discussing about the end eye. So when we come to when we change this reinforcement area into reinforcement ratio, that is 0.24. That means rho, which is equal to the area of the steel divided by, that is the BD, where B is the width and D is, it is the effective depth. So just we can calculate the rho. So rho becomes 0.24. Here it is 0.24 in percent, and this one is also, it is 0.24 in percent. So this is the reinforcement ratio which is required at the end eye. That means at the left support of the beam. So when we come to at the middle portion, so this is, the middle portion. So how much reinforcement area is required? It is 498 at the top and 498 at the bottom. So here we can take section BB here. So we can say section BB. So we can draw section BB. So here we have a neutral axis here. So here we have axis minus 2 and this is positive 2. So above the neutral axis, which is positive 2, and below the neutral axis it is minus 2 zone. So how much reinforcement area is required? 498. So at the bottom, 498 millimeter square. And similarly at the top, how much required? It is 498 millimeter square. So when we convert it into the reinforcement ratio, which we can apply similar area, that similar formula. So it becomes 0.24 and it becomes 0.24. How it comes? Simply we can put 498, which is divided by B is, it is 350 into D is, which is the total depth of the beam is, it is 600 minus the cover, which is 25, minus the diameter of the strap, which is 8. So minus half the diameter of the member, which is 16. Sorry, which is 16 over 16 divided by 2, it is 8. So it becomes how much? 0.24. 24. So just you can calculate it. So, and also integer, which is in similar manner also here we can say section CC, and similarly we can draw section CC. Here it is positive 2 and here it is negative 2. So the reinforcement area which is required at the top parts of the right support becomes, how much is it? It is 498. That is 498. How much in rho equals to how much is it? It is 0.24. And when we come to also the bottom part, it is similar. That is 498 millimeter square. So how much is 0? It is 0.24, which is 0.21. So here the beam needs uniform reinforcement at the top as well as at the bottom, both at the support and at the span of the beam. So having this in mind, just we can prepare detailed working drawing of this specified beam. Okay, when we come to the movement in that is MED3 and MED2, that we can here this is the movement about the axis, and we'll have also the movement about the, here we have, here this is the beam and this is axis 2 and this is what, axis 3. So the movement about axis 3 is how much? Here the moment which is at in the eye, it is minus 54.8 at positive 2 axis. That means here this is positive 2. Sorry, this is positive 2 and this is minus 2. So the moment at in the eye, suppose here we have a beam at in the eye. How much is it? The moment which is minus 54. That means the moment diagram looks like this, just like this. So here this moment is, it is minus 54. And similarly at the bottom, how much is it? It is positive 27. Here at the bottom, that means at the this bottom here at this support, how much is it? It is minus 27. Minus 27. Here, I mean, sorry, positive 27. And when we come to, that means the region between this and what? This. So when we come to also the middle one, that is minus, that is MED, which is equal to minus 30. At the middle here, at this part, minus 13. And at the bottom, that is positive 18 here at this one. And also at the right support here, it is minus 30, and at the bottom positive 6. So just we can take this result for the calculation of reinforcement area. So when we come to also the shear design, the shear reinforcement for major axis, that is VD2. VD2, suppose here we have a beam, this is 2 and this is what? It is 3. So the reinforcement has to be provided along the major axis. So which one is the major axis for this beam? So we need to provide the strap along the major axis. That is axis T2 is, it is the major axis. Okay, now let's proceed to, sorry. And now the here the design shear force Here we have a beam. This is in the eye and this is J. So in the eye uh, has a shear force of it is 32. It is 32. That is positive. And in the and also in the eye station location at 0 and at the span which is around here 0.0054. So the shear force at the span zone is what? It is insignificant. So it needs minimal reinforcement. And the shear force closer to the support is it is higher with respect to the mid span. So it needs closer arrangement of stirrups. And also similarly here it needs also closer arrangements or closerly spaced shear reinforcement here. So how much is it? How much shear force exhibits at the joint J? That means it is around 21.89. That is 22. That is positive 22. So here this and this, what you call it is the critical shear force, which will be applied to beam. And similarly here the integer now this is the station, that means the length. So the length of the beam here, this is the station 0 and this one is the station which is 7.712 meter. So the length of the beam is it is around 7 meter. Okay, now when we come to also the torsion reinforcement, when we come to the torsion reinforcement, here the shear rebar, that means a torsion per spacing which is 0. So there is no any torsion here. So no need of providing torsion reinforcement. Okay, now so which load combination governs in designing of shear and in designing of beam? So we can see it. So when we come to the torsion, the service load is it is the controlling one. Okay, this one is it is the controlling one for torsion, and for shear force, which combination is the controlling one? It is the gravity load. And also when we come to the flexural design, which combination is the governing one? It is the gravity load. So the first combination is the controlling and the governing load combination for the design of beams. Okay, so having all those results in mind, we can go to the spreadsheet and we can prepare the detailed working drawing for this specified beam. So I have already prepared a spreadsheet which will be used for the designing of beams. So now here, this is the beam design. It is the ductility class medium. So we have already discussed about the ductility class of our structure. So the ductility class is categorized under ductility class medium because it is a reinforced concrete structure. So for this ductility class medium structure, we have already used the basic behavioral factor, which is 3 for non-coupled system before we applied the reduction factor. And when we come to also the grade of the concrete here, that is FCK, which is equal to 25, or that is FCU, it is how much? It is C30. So C30 concrete were used for the designing of beams and slabs. So we have already applied during the modeling of beams and slab. And the cover, it is 25 millimeter. So based on this provided data, we can determine the mean tensile strength of the concrete. That means the FVCTM, which is equal to 0.3 times FVCT to the power of 2 over 3 for concrete class, having the cube strength less than 60. So Based on this, FCTM, which is equal to 2.564 Newton per millimeter square. So FCD, how much is it? It is 40.16 Newton per millimeter square. That is the design strength of what? Concrete. So FCD, which is equal to alpha CC times FCK over gamma of concrete. So what does alpha CC? What does gamma of concrete? We have already discussed during the design of column. So you can come back to the tutorial part 80 and you can see the detailed description of these parameters. And when we come to alpha CC, which is 0.85, and gamma of concrete, which is equal to 1.5. So, based on all those results, we can calculate the design strength of concrete. So, when we come to the reinforcement bar, that is FYK, which is equal to 500 Newton per millimeter square. So, this is the yield strength of steel. And rho prime, the strain of the steel, and this parameter, all those parameters are incorporated during the design of beams in ETABS. So when we come to the beam geometry data, that is the height of the beam it is 600. That is the depth of the beam is 600 millimeter, and the width is 350 millimeter, and the critical length which is equal to 600, meaning the critical length at the support equals to the depth of the beam according to the Ethiopian Building Code of Standard 8 and the European Building Code of Standard 8. That means here this is what? L critical. So here this is L critical. So L critical equals to how much? L critical is equal to the height of the beam, HW, meaning the depth of the beam. This is for ductility class medium. For the ductility class high, we can use L critical 1.5 times the height of the wall, because we need to increase the critical length for ductility class high. As seismic is critical, the strength of seismic is higher with respect to the ductility class medium. So our structure is categorized under ductility class medium. So we can provide the critical length which equals to the depth of the beam. And now here this is the width of the beam, L critical. So it's equals to 600 mm. Reinforcement area, the main top bar area at the support, which is 498. That is, we have already extracted from ETABS. And the main bottom bar area at the spot, that is 498 millimeter square. So all those results are taken from ETABS output. The diameter of the main bar, which is 60 mm. So it may be 60 mm or it may be 20 mm. So it depends on the magnitude of movement. And the number of bars at the top, it becomes that is 3 60 reinforcement bar. And also the number of bars at the bottom becomes 3 diameter 60 reinforcement bar. So based on the number of bars and the diameter of bar, we can calculate the area of reinforcement ratio. That is the reinforcement ratio. So the reinforcement ratio, that means rho, which is equal to the area of the steel. That means this area divided by the width of the beam into the effective depth of the beam. So it provides this value both at the top and at the bottom. So shear rebar at in the eye, that means at the left support, it equals to 280 mm square per meter. So this is taken from ETABS. So now let me come to here. Here, this is the shear reinforcement area per meter width. and this one is at the span, and this one is at the support. So both the support and the span needs the same amount of shear reinforcement area because the beam is not that much highly stressed. So now let me come to the spreadsheet. So here, it is 280, 280, 280. So here we have three locations: the left support, the span, and the right support. The diameter of shear rebar is 8 millimeter. The spacing as per the actual shear rebar is 300 millimeter. How it comes? Now let me go to the. Here I have already prepared a spreadsheet to determine the spacing of shear reinforcement. Here we have a spreadsheet which provides the spacing of reinforcement having the area of shear reinforcement. So now let me come back to ETABS. That is the rebar ASV per spacing is 280. So here I have at the link tab. Then I need to use to leg strap. So I have to provide here 0.28. So how much is it? It's 300 millimeter for 8 diameter. So now come back to here. That is 300 mm. That means the spacing as per the actual shear reinforcement area. So based on the code, it is 128, and uh, that means the Ethiopian building code of standard and the European building code of standard suggested the maximum spacing of shear reinforcement bar. That means it is 8 times Dale 24 dBW and 225 millimeter. So here and here there is also an additional, that is the depth of the beam by 4, meaning height of the wall, that is depth of the wall over 4, 24 the diameter of the bar, and 8 times also the diameter of the main bar. This one is the diameter of the shear reinforcement, and here this one is 225. So we can take the minimum of all this value. So here the height of this is clearly indicated here. That means the spacing, this spacing at the critical zone should not be exceeding the depth of the wall over 4, 24 times the diameter of shear reinforcement, and 8 times the diameter of the main bar, and 225. And this one is for ductility class medium. And if it is in ductility class high, so we need to use 6 times the diameter of the main bar. That means it becomes reduced. And also in the case of the fourth option, that is in the case of the ductility class medium, we can take 225, and in the case of ductility class high, we can take 175 mm. So in the case of ductility class high, we need to use a closer stirrup. So here, so all both values are calculated here. So we need to take the minimum of the four results. So spacing must not exceed the minimum of the local ductility requirement. That means 128, this one. And spacing must, the governing spacing becomes, it is 128. So provided spacing at the critical region is, it is 120 mm. So we have to use S, which is equal to 120 mm. 120 mm at the critical zone. Here also S which is equal to 120 mm. So the maximum spacing at non-critical region, that means the spacing here, that is we can take S2. S2 will be, just we'll come back to the spreadsheet, that is 0.75 times D. This is the maximum spacing of stirrups at non-critical zone, meaning at this zone. So it should be less than 0.75 what times D. So this is the effective depth. That means 0.75 into 600 minus 25 minus 8 minus also 8. So it becomes, I think, 375. Okay, now let me come back to the spreadsheet. It is 420. So this becomes 420. It's 420 mm. So we can use the provided spacing and not critical zone, that is 200 mm is sufficient enough. So S2 here, S2 has to be what? 200 millimeter, and here S at this zone will be this 120. So the minimum reinforcement ratio at the tension side will be 0.5 times FCTM, that means the tensile strength of the concrete over the yield strength of the steel. That means 0.02565. So this is the minimum reinforcement area ratio. This rho mean, this rho mean must be less than rho provided. So rho provided, that is 0.03, is greater than 0.025. So the provided reinforcement area is greater than the minimum reinforcement area which is specified in the code. So our provision is adequate enough. So we can provide 6 diameter 16 which have been already provided here. 6 diameter, I mean 3 diameter 16 reinforcement bar with the total reinforcement area of 602.88 millimeter square. So also we need to check the minimum requirements of the reinforcement area at the compression zone of the section. So here we have 3 compression zone of the section. That means, suppose this is the section. So here we have the beam. Here this is our movement diagram. So in the eye, the top part will be in tension, and here the top part will be in tension, and at the span the bottom part will be in tension. So at the span the top part will be in compression, and at the support the bottom part will be in compression, and at the support the bottom part will be in compression. So the reinforcement area at the support, where the section is exposed to compressive stress, then that means the area of the steel at the bottom support, at the bottom of support, must be greater than 25% of the span moment, the span reinforcement bar. Here it is clearly indicated here. We can come back. At this one. That means the area of steel mean top span, which is equal to the area of the top support divided by 4. That means 25. We need to use at least 25% of the support moment at the top parts of what? The top span, that means at the compression zone. So here we need to use the area of steel at the top part must be greater or equal to the area of steel at the support. That means the compression reinforcement at the top of the span must be greater than the 25% of the area of reinforcement which will be provided at the support. And this is one of the requirements of the Codal provision. And when we come to the area of the steel minimum at the critical region, that means here we have critical region here, that is L critical, and here we have also L critical. So the area of steel minimum, the area of steel minimum at the critical region, which is equal to 50% of the area of steel at the top. That means we have to provide a minimum reinforcement area at the bottom of the support, meaning at the compression zone of the support, which is equal to 50% of the area of the steel, which will be provided at the top, meaning at the support. So we need to use 50%. That is the 50% of area of the steel at the support. So this is the minimum provision. And also when we come to the area of the steel minimum at the support bottom, here at the support bottom, meaning this is the critical. Here, this is L critical. So L critical is, it is, how much is it? It is 600 millimeters. So within 600 millimeter length, we need to provide a minimum of 50% of the area of the support which will be provided at the top. So within it is 60 mm. But in L over 3, in L over 3 region, we need to provide, how much is it? It is 25% of the reinforcement which will be provided at the span. So based on this Codal provision, so based on all this Codal provision, we can check the provided reinforcements are as per the Codal provision or not. So here at the span top, that is compression steel, should be greater than how much? Should be greater than to diameter of 40, which is equal to 308 millimeter square. This is also specified in the code. And the area of the steel bottom at the bottom of supports, that means at L over 3, meaning this one, which is at the compression zone, the reinforcement must be greater than to diameter 40, which is equal to 308 millimeter square. So we should not use the reinforcement area less than 308 millimeter square at the compression zone of the section. So we have already provided 3 diameter 16 reinforcement bar. That means this provided reinforcement area is greater than the minimum reinforcement area which is provided in the code. So our provision of reinforcement is okay. And all this, so rho max, which is equal to rho prime plus, here we have also the maximum limit of reinforcement area. So we should not use the reinforcement area which will be greater than the maximum allowable reinforcement area specified in the code. So this rho max, which is equal to, sorry, where is it? Okay, here, that is rho max, which is at the critical region, rho max at the critical region, which is equal to, that is rho prime plus 0.0018 FCT into mu phi times the strain times the design strength of the steel, that is FVD. So this rho max is provided for every grade of concrete in the code. So we can take from that, or ETABS can take into consideration the maximum reinforcement area while calculating the required reinforcement area. If the provided reinforcement area is greater than the maximum allowable reinforcement area, so ETABS will provide an error. So in this case, as the ETABS didn't provide us an error, so our provision of reinforcement area is less than the maximum allowable reinforcement area specified in the code. So the provision of the reinforcement area for these selected beams at the support and at the span is adequate enough. So this is, I think, all about the today's tutorial. So for further, here we have the spacing of, I think, here we have the detailing and the dimensioning of the primary seismic beam. This can be taken from the code. That means rho mean at tension side, which is equal to, for the ductility high and ductility class medium, 0.5 times FPCTM over FYK. And for ductility class low, just we can use this formula. And rho max at a critical region, that means with a 600 millimeter length of the support region, we can use this rho max for ductility class high and ductility class medium. This rho max can be taken into consideration while calculating the area of reinforcement by using ETABS. So if it exceeds the rho max, then ETABS will provide an error. So area of steel minimum at the top and the bottom. We need to provide at least two diameter 40, that is 380 millimeter square reinforcement bar at the top and at the bottom. So this is the minimum reinforcement which has to be provided for the beam. And area of steel mean the minimum steel reinforcement at the top span, that means at a compression zone, which is equal to the area of steel which is provided at the support divided by 4. This is for ductility class high. And for ductility class medium, it is not specified clearly. That means, so we can use the ductility class high provisions for ductility class medium. So we can come to here, area of steel minimum at the critical region, the bottom, that means at the compression zone of the support. So we need to provide 50% of the area of steel which is used at the top support for both the ductility class high and the ductility class medium. And the area of steel minimum support bottom, that means here this one is at the critical region. Look here, the difference is this is at the critical region bottom, and this one is at the support bottom. So at the support bottom, we need to use 25% of the area of steel, which is going to be used at the bottom of the span. Sorry. So this is the Codal provision which is provided for the design of beams. So here there is also the transverse bars provision here. So the spacing of the stirrups outside the critical region is 0.75D, which I've already discussed before, and the spacing of the stirrup should be less than 0.75D, and the shear reinforcement ratio, which is equal to we can use this formula for both ductility class high up to ductility class low. And here in critical region, that means the diameter of the strap uh, should be greater than 6 millimeter, and the spacing should be less than 6 dBl, 24 dBw, 175 for ductility class high. But for ductility class medium, we can use 8 dBl, 24 dBw, 225 mm. BW means it is the diameter of the strap. dBl means the diameter of the main bar. So we can use the minimum of the two, the three. Here we have also h, the depth of the beam over 4. So we can add this one. The fourth option is missed here. And so here this is the VED, and this is the VRD max, and this is the VRDS, and this is the VRDS. So all those, if the VED is greater than the VRD, so we need to provide shear reinforcement because the capacity, the shear capacity of the concrete is exceeded by the applied shear force. Okay, now this is all about for today's tutorial. So if you like my video, don't forget subscribe my channel, and also don't forget share my videos to your friends so that your friends will be getting more relevant videos which have been already prepared regarding to the modeling and designing of this 20-story building using ETABS 2016 as per the Ethiopian Building Code of Standard and the European Building Code of Standard. So, if you have any questions regarding to the modeling and designing of reinforced concrete structures and steel structures, you are all welcome. And don't hesitate also providing me comments and questions in my commenting box so that I will be answering your questions and your comments within a short period of time as much as possible. So if you want to get an immediate notification for the uploaded videos, don't forget pressing the bell icon. So this is all about the today's tutorial, which is tutorial part 19, focusing on the design of beams in 20-story building. So we can design the rest beams in similar manner as these selected sample beams. So see you next time with the design of shear walls. Bye bye.